Here we have a wagon that's connected to a spring, which is relaxed at x equal to 0. And a boy is going to pull the wagon forward with a force of 500 newtons at an angle that makes up a 3, 4, 5 triangle. The spring constant is 800 newtons per meter, and we're asked to predict the motion with and without friction acting on it. So if we look at this, we have 500 newtons, which we can break down into 400 newtons in the x and 300 newtons in the y, based on the 3, 4, 5 triangle for this. And what I'd first like to find is the static location where the wagon would be in equilibrium. And at that location specifically, we would have 400 newtons pulling forward, and the spring would have been stretched out using Hooke's law, some kx value. We have no friction yet. And for equilibrium, we can say then that the sum of the forces in the x is 0, and that kx is equal to 400, or x is equal to 400 on k, which is 800, which will give us 1/2 of a meter. So we find then for this system that xeq is 1/2 of a meter. That's if the boy pulled this forward very, very slowly. When he reached about 1/2 of a meter, it would stop and he'd be in equilibrium at that location. For the next case, let's look at what happens when the boy starts at rest and runs forward, pulling the wagon with 400 newtons the entire time. How far can they make it if they take a dynamic run at this? Well, this is a classic example of a work energy theorem where we can define this. We can define the energy in the beginning, which would be here at 0, as 0. Nothing's happened yet. The spring hasn't been stretched. E final, we've pulled the wagon out some distance, and the wagon then stops out here. So the final energy in this scenario would be 1/2 k x max squared. All the energy is in the spring, and the work done would be the force, 400 newtons, times the distance x, and it would be positive because it's putting work into the system by moving it. So if we apply that to our work energy theorem, we get Fx is 1/2 kx squared. And solving this, we find that x is 0 for one of the solutions, and that x2 would be 2f on k, which is 2 times 400 over 800, which is 1 meter, or exactly twice the xeq value that we had up here. So the boy pulls the wagon forward and can reach, if it takes a running start at it, an x max of 1 meter out to here. Now, an interesting question that we could ask is, once the boy is there, will he stay there? And we could answer that quickly with a free body diagram. The boy is pulling forward with 400 newtons, and the spring force is still acting. It would be kx, and that would be 800 times 1 meter. So we have 800 newtons acting in the reverse direction. The boy is going to be pulled back very rapidly with a large acceleration. So the boy is going to move out to here and will not be able to stay there. He'll reach that point and then it's snapped back. And the second part of that solution tells us how far back he'll go. So what will happen is the boy will run forward and then get snapped back, and then run forward again and then get snapped back. And we can see that, or at least predict that possibly this thing will behave in simple harmonic motion. There is a spring involved, although it's more complex because of the force as well, but it does appear to be behaving in simple harmonic motion about the equilibrium point 1/2 of a meter. Let's see if that's true. We found that x eq was f over k, and x max was 2x eq so far. And we'd like to check for simple harmonic motion. And an interesting way to do that with conservation of energy is to again apply the work energy theorem. But let's apply it to some arbitrary location here, x, where the wagon's still moving with some velocity v and has stretched out the wagon spring a little bit. So what we would have then is E0 is still 0. Ex would be 1/2 mv squared plus 1/2 kx squared. We're still running with the wagon and we're still stretching the spring. And the work done would still be force times distance. We put all these together, we have fx 1/2 mv squared plus 1/2 kx squared. And we can clean this up a little bit algebraically, multiplying through by a 2 and dividing through by an m. Now let's take the derivative of this in time, and we'll get 2f over m constants times x dot, the derivative of x, is, now v is really x dot, in this case, squared, so we'll replace that. And the derivative of x dot squared would be 2x dot times x double dot plus k on m times 2x x dot. And if we look at that, we can divide through by x dot. We can also divide through by 2. And if I rearrange this slightly, we get x double dot plus k on m x is equal to f on m. And we can recognize this as a second order non-homogeneous differential equation. But what is interesting here is that is our simple harmonic motion sinusoidal solution. And what we have over here is a forcing function, which is a constant that's driving that. And we know that for non-homogeneous types, x general is equal to the homogeneous solution plus the particular solution. And the reason we have the homogeneous in here is we often can just think of it as having a 0 here, plus 0. So our function, whatever it ends up being, has to generate the homogeneous part that we've seen in the past, along with this constant as well. So let's start with the particular. We'll assume that the particular looks something like this constant, so it's going to be a t plus b. And it's a good idea to at least go one level higher than the constant itself, just to see if other terms might be there. X dot particular would be a, and x double dot would be 0. And we plug them all into here, and we get 0 plus k on m times a t plus b is equal to f on m. And since there's no t functions over here, we can say that a equals to 0, and we end up with k on m times b is equal to f on m. And we can bring the m on k over here, inverting it. The m's drop out, and we find that b, our constant here, is going to be f over k, which I can bring over to here. And that will be our particular solution. To go after the homogeneous solution, we can now put this whole thing together. And again, we know that this is going to be a sine and a cosine form. So x general will be c sine of omega t plus d cosine of omega t plus our f on k variable that we found. And we can apply a boundary condition here if we like. At t equal to 0, x was 0. The boy started at rest and ran from that location. Sine of 0 is 0. Cosine of 0 is 1. And we find that d is equal to minus f on k. If we take the next derivative of this, we get c omega cosine of omega t minus d omega sine omega t plus 0. And we have another boundary condition here. At t equal to 0, x dot was 0. It started from rest. So sine of 0 is 0. Cosine of 0 is 1. And we find that c is equal to 0 from that. So this term doesn't exist. And with that, we have our solution. So our final solution is that x is equal to minus f on k cosine of omega t plus f on k. And from here we can see that we have an oscillator with an offset on it. And recall that f on k is actually x equilibrium. If we look at this, at t equal to 0, x will be, this will be 1, minus f on k plus f on k, which is 0. We're going to start back here at rest, and then the boy is going to run forward from here. Here's the equilibrium point. And out here at some point would be x max. At t equal to pi on omega, the cosine will be minus 1, and we'll get f on k plus f on k, which is 2f on k, which is 2 times x equilibrium. So we find then that this does predict that it will oscillate back and forth between these locations. The behavior is simple harmonic motion. The omega here is this, so we find that omega squared would be k on m, or omega is the square root of k on m. We also know from simple harmonic motion that the period of this oscillator would be 2 pi on omega, which would be 2 pi times the square root of m on k. So that's how long it would take for the child to oscillate through one full period of running all the way out and then getting snapped back to where they started from. And even with the forcing function in here, we still get the same time period for this. So it is a harmonic motion event. And there's a way to show it using conservation of energy to build the differential equation that drives that solution. Let's take a look at case C now, where there's friction involved. And we have that mu sub k is 0.5. And to start this, we need to come up with the frictional value. So a quick free body diagram up here. We have mg acting straight down. We'll have the normal acting up. We also have this 300 newtons here acting up as well, so don't forget that. Summing the forces in the y is equal to 0. We have n plus 300 up equals 490 down, which is 50 times 9.8. So the normal force will be 490 minus 300, which will be 190. And therefore the frictional force will be mu k times Fn, which will be 1/2 times 190. So we have 95 newtons worth of friction acting on it. So let me record that over here. The friction is 95 newtons. And let's apply the work energy theorem once again. So these locations here where the energy is in one form are called nodes. and they're actually quite useful. Right here we have no energy at all. That's the start point of the system, so that's a node. And when we reach this location, 100% of it is in the spring. So that's another node. And when we're solving for spring-driven problems, and other problems too, looking for these nodes where all the energy is in the spring or in kinetic only or at a 0 point are very, very useful. So it turns out both of these locations will be nodes for us. It starts here at E0 is 0. It has no energy initially. It's then going to get pulled out to here someplace and stop at some location X. So the energy at X will be, again, 1/2 k x squared, where it stops at that location. And the work will be the force by the distance. Now for this force, again, let's look at our free body diagram. The boy is pulling this thing forward with 400 newtons, and now we have friction acting in the reverse direction of 95 newtons. So there's a net force of 305 newtons in the forward direction. So the work being done is now 305x. We have 305x, the work, is equal to the energy, 1/2 k x squared, at the final position plus none of it in the beginning. And we'll find again that x1 is 0, and x2 is 2 times 305 divided by k, which is 800. So x2 will be 0.7625 meters. So if we look up here, this was a half, there's 1. It makes it just a touch past here about where this is shown. So there becomes, we'll call XC for case C. And that's as far as they could go. Now again, we can ask the question, will it stay there? Well, let's see a quick free body diagram. We have 400 newtons acting forward. The wagon's going to reverse and try to go backwards, so this friction is going to turn around now, which was 95 newtons. And in this direction, we have the spring force of kx, which will be 800 times 0.7625, which is 610 newtons in the reverse direction, of which we have 495 in the forward direction. So we're not going to be able to stay here, we're going to return. Let's try to find out how far back it can go. So for case D, how far back will it go? So it's going to snap back. Will it reach the equilibrium point? Will it go past the equilibrium point? Can it reach back to x equal to 0? Let's see if we can find out. Well, again, the work energy theorem, the energy initial this time will be 1/2 k x c squared, because we're starting from here. The energy final will be 1/2 k x final squared, and there'll be no kinetic energy. It'll stop at this location as well. So again, another node. Next, we can find the work as the net force acting on the block times xc, the starting location, minus xf, which is where it ends up. So that's the distance that it's going to move. Now to find this net force, again, let's look at the free body diagram of our little block. The boy is pulling with 400 newtons in this direction. And because we're on our way back, the friction will also be in this direction of 95 newtons. And because it's opposing the motion, it's stealing away kinetic energy. Right? This box is trying to speed up, and the friction plus the boy are slowing it down. So all of this represents negative work being done on the system in this case. So this will be negative when we apply it. This then is negative 495 newtons for that. And let's clear some space. So work will be energy final minus energy initial. We have negative 495. XC we know, 0.7625 minus X final. That's equal to the energy final, which is 1/2 k x final squared, minus the energy initial, 1/2 k xc squared, where again xc we know it's 0.7625. From here we'll get negative 377 plus 495x, I'll just call it x for now, is 400 x squared minus 233. Note that this is a second order polynomial, so let's rearrange this starting from here. We have 400 x squared minus 495x minus 233 plus 377 is equal to 0. And we can use the quadratic equation, and we'll find that x1 is 0.468 and x2 is 0.769. And we have to use logic to determine which of these is valid. Now we started at 0.762, so this one can't be accurate. So it turns out that's how far back we'll return. So that's equal to x final. Looking at our diagram up here, it slides back and it comes just a bit past here at 0.468, just below the half. And again, we can ask the question, will it stay? Quick free body diagram, we're pulling forward with 400. We have a spring force here of kx, which will be 800 times 0.468, which is 375. And then we have 95 newtons worth of friction, where if the boy is trying to pull it forward, friction will act against him, so that'll be over 400, it won't move. And if the spring were trying to pull it back, the spring's not strong enough. So it turns out, at this point, it's going to stay at rest and it'll stop. So the boy would stop here. So we find that friction will grind it to a halt after one oscillation. So using conservation of energy, we're able to predict the location. When we have work that becomes a little bit more complex, it's not uncommon to get a polynomial out of it that we have to use the quadratic equation for. And also there are ways to take the energy equation and turn it into a differential equation by taking a derivative of it. Thanks for watching.